doing my presentation on adopting a performance-based safety design on safety instrumented system implementation, and that's based on the ISA 8401-2004 standard. Maybe a little bit first about Georgia-Pacific Chemicals. Georgia-Pacific Chemicals is a manufacturer of resins and specialty chemicals. The biggest product volume goes into building products. Talking about plywood, glue that glues plywood together, or OSB, or other building products. So that's where the largest volume is. But we make all kinds of other chemicals as well. The presentation covers the safety life cycle management as it is defined by this standard. And let's go forward. And what we developed is best practices for managing the safety instrument system life cycle based on the standard. The presentation covers description of activities, requirements, and expectations for managing the safety instrument system life cycle, and including the management system requirements and organizational requirements. The safety life cycle defines a consistent, systematic, and detailed, well-documented, and auditable approach to safety instrument systems implementation. Just a quick look into the ISA 840001-2004, which actually is modified from the 61511 European standard that was mentioned just a little while ago. This standard defines the activities and requirements for safety instrument systems life cycle. A little safety instrument system definition here. SIS safety instrument systems are one of several risk reduction measures that are commonly used on hazardous processes to minimize the risk of death or injury to personnel, harm to the environment, damage to the plant equipment, or loss of production. Some examples of other risk reduction measures are process design, of course, relief valves, rupture discs, human intervention, fire protection systems, and so on. The SISs, safety instrument systems, are never used as the only risk reduction measure and are usually used only as the last resort if other available risk reduction measures are not sufficiently reduce the risk to the acceptable levels. Based on the standard, there are three phases on the safety life cycle management. The phases are analysis, realization, and operation. We're going to take a look at each of these next. The analysis phase, all the potential risks and their consequences are identified, and the layers of protection are analyzed. This leads to development of non-SIS protection layers, and finally to identification of the need for a SIS, and including the requirements for the SIS. In other words, you identify the hazards, you select the SIL, safety integrity level based on the risk analysis. You can use different methods of coming to that, LOPA or other methods. You develop the safety requirement specification, SRS, and verify the SIL level of the proposed design. And then at this phase, you also make the selection, in many cases, make the selection of your logic solver and other parts of your safety instrumented system. The other part of this is the definition of organizational responsibilities and skills that are required. So you would define the training needs for the operations and maintenance. You would put together a document management system to manage and keep record of all the documents for the system, such as standard operating procedures, management of change documents, training records, calibration records, and so on. The skills and responsibilities are also defined, and at all levels of organizations. So plant manager, operators, maintenance, and then engineering and environmental health and safety also have responsibilities. The next phase is the realization phase. The installation is done, of course, based on the validated design, but the SIS commissioning includes confirmation that equipment and wiring are properly installed, the energy sources are operational, all instruments are properly calibrated, field devices are operational, the logic solver itself and all the I/O related to that are operational, and all parameters of the configuration are validated. To do that, you need to use a comprehensive commissioning document, and that will make sure that nothing is missed. And it also provides a document to be put into your document management system for later. We're going to talk about the training in a little bit, but talking about the validation, it includes the validation of I/O, where all the physical and soft connections of all inputs and outputs associated with the SIS are checked, and a functional validation where all programmed logic is checked against the SRS safety requirement specification. Also, training plan needs to be developed for operating personnel interfacing with the safety instrument system. A combination of training methods can be utilized. We developed computer-based training modules. We have had hands-on training with the simulator before the system was installed in the field, and then of course develop all the standard operating procedures for the system. The maintenance personnel training included also CBTs and Honeywell Safety Manager Maintenance School and standard maintenance procedures for safety system. The engineering and environmental health and safety resources training included CBTs, Honeywell Safety Manager Maintenance and Safety Builder Configuration School, and some periodic higher level training as well. The last phase, which is the longest, timeline of the life cycle, safety life cycle, is the operation phase. The operating procedures are finalized and written to explain the correct and safe operation of the safety instrument system. These procedures cover the hazard that is protected with this SIS system against, and also the operation limits for the and all the safety implications of exceeding them, and then how the SIS functions to take the process to a safe state, and of course the correct response to any safety instrument system alarms and trips. The maintenance program includes regularly scheduled functional testing, preventive maintenance like calibration, valve operation, and so on, and repair of all detected faults. A training plan was also implemented to assure that there is ongoing capabilities of operations and maintenance resources. So the training will be ongoing. And periodic functional testing is also required to assure that the desired SIL level is maintained. And these tests, of course, could include, partial testing, valve testing, full testing, whatever parts you have in your safety instrument systems. And any deficiencies that are found during testing have to be fixed and documented. The bypassing of any part of the safety instrumented system removes that system as a layer of protection, and therefore is not allowed in our application. The audits can be administrative system audits, documentation audits, understanding of system, interviews, and those kind of things. And the audit types that we have defined are self-audits, independent audits, inspections, safety visits, and safety instrument system surveys. System modifications may be required for many reasons, like technology quality improvements, equipment redesign, and so on. So all changes have to be managed through management of change procedures. And everything has to be documented through that procedure as well. The safety instrument system MOC, management of change procedures, are used to initiate, document, review, and approve all the changes. And also, when it comes time to decommission the system, it will be also done through that same procedure. A little recap: the approach based on the standards has very high resource demand because you have to develop all these detailed documentation, all the training, implementation planning, testing planning, commissioning, documentation, and life cycle management planning and ongoing management. So there's got to be very strong support from management side so that you can do these things the right way. I think that that's it for me tonight.